Hello everyone. Myself Mr. S.M. Ganwat working as Assistant Professor in Mechanical Department at Sharad Institute of Technology College of Engineering Yadrao Ichalkaranji. We are discussing unit number 1, that is structure of materials. In this session we are going to discuss part 4 of structure of material. In part 4 of structure of materials we are going to discuss the crystallographic points and direction. The first point that we are going to discuss is the point coordinate with example. And the next point that we are going to discuss is the crystallographic directions. Now we are going to deal with the next point, that is crystallographic points, directions and planes. When dealing with crystalline materials, it often becomes necessary to specify a particular point within a unit cell, a crystallographic direction or some crystallographic plane of atoms. Labeling conventions have been established in which three numbers or indices are used to designate point locations, directions, and planes. We are going to repeat this particular point once again. When dealing with crystalline materials, it often becomes necessary to specify a particular point within a unit cell, a crystallographic direction or some crystallographic plane of atoms. Labeling conventions have been established in which three numbers three numbers or indices are used to designate point locations, directions and planes. The basis for determining index value is the unit cell with a right-handed coordinate system consisting of three x, y and z axes situated at one of the corners and coinciding with the unit cell edges as shown in earlier figure. For some crystal systems, namely hexagonal, rhombohedral, monoclinic, and triclinic, the three axes are not mutually perpendicular, as in the familiar Cartesian coordinate scheme. Now, we actually start with our first point, that is point coordinates. The position of any point located within a unit cell may be specified in terms of its coordinates as fractional multiples of the unit cell edge lengths. Once again, I will repeat this particular point. The position of any point located within a unit cell may be specified in terms of its coordinates as fractional multiples of the unit cell edge length, that is in terms of A, B and C. To illustrate, consider the unit cell and the point P situated therein as shown in figure. We specify the position of P in terms of generalized coordinates Q, R and S, where Q is some fractional length of A along the axis X, R is some fractional length of B along the y-axis, and similarly for S. Thus, the position of P is designated using coordinates QRS within values that are less than or equal to unity. Furthermore, we have chosen not to separate these coordinates by commas or any other punctuation marks, which is the normal convection. I am going to repeat the same point coordinate system as the position of any point located within a unit cell may be specified in terms of its coordinates as fractional multiples of the unit cell edge length. That is, we are going to represent it in terms of A, B and C. To illustrate this particular concept, consider the unit cell and the point P situated therein as shown in figure. We specify the position of point P in terms of generalized coordinates Q, R and S, where Q is some fractional length of A along the x-axis. R is some fractional length of B along the y-axis, and similarly S is some fractional length along z-axis. Thus, the position of point P is designated using coordinates Q, R, S with values that are less than or equal to unity. Furthermore, we have chosen not to separate these coordinates by commas or any other punctuation marks, which is normal convection. This is all about the point coordinates system in crystal structure. And the figure is going to show you the manner in which the Q, R and S coordinates at point P within the unit cell are determined. The Q coordinate, which is a fraction, corresponds to the distance QA along the x-axis, where A is the unit cell edge length. The respective R and S coordinates for Y and Z axis are determined in similar fashion for determining the coordinates for point P. This is all about the point coordinate system. Now we are going to discuss this particular concept of point coordinate with one example. Location of point having specified coordinates. We are going to see the example for the unit cell shown in the accompanying sketch A. Locate the point having coordinates 1 by 4, 1 and 1 half. The figure A is going to show you the unit cell having lengths of each edge are 0.48, 0.46 and 0.40. According to this unit cell edge length, you are supposed to determine the point P in this particular unit cell. Also, you are provided with the coordinates of point P, that are Q, R and S. Q is going to represent you the coordinate for point P in x direction. R is going to represent you the coordinate of point P in y direction, and S is going to represent you the coordinate for point P in Z direction. Now we are going to correlate this particular Q, R, S, which are the coordinates of point P, with the edge lengths of unit cell. In figure A, the edge lengths are given to you, and accordingly you are supposed to locate the point P with respect to the coordinates 1 by 4, 1 and 1 half. From sketch A, the edge lengths for this unit cell are: A is equal to 0.48, B is equal to 0.46 nm and C is equal to 0.40 nm. Furthermore, in light of the preceding discussion that we have already discussed, the fractional lengths are Q, R and S. Q is equal to 1 by 4, R is equal to 1 and S is equal to 1 half. These are the fractional lengths associated with the point P. Therefore, the first we move from the origin of the unit cell point M, that is shown in figure. The QA is associated with the x direction. Therefore, the QA will give you the value as 0.12 nm units along with the x-axis to point N as shown in figure B or sketch B. Similarly, we are going to proceed for RB, that is 1 into 0.46 nm. The value of R is 1, the value of B is 0.46, which will give you the 0.46 nm parallel to y-axis from point N to point O. Finally, we move from this position to SC. SC will be equal to 1 half into 0.40 nm. The coordinate of S is 1 half and the edge length of unit cell C along z-axis is 0.40. Therefore, this value will give you 0.20 nm units parallel to z-axis to point P as noted again in sketch B. This point P then corresponds to 1 by 4, 1 half point coordinates. This is the solution to determine the point coordinate for given coordinates. We have located the point P as the coordinates are given to us. According to these coordinates, we have located the point P. Also, we are going to repeat this particular process once again. The figure A is going to show you the unit cell having edge lengths A is equal to 0.48 nm, B is equal to 0.46 nm, C is equal to 0.40 nm. These edge lengths are along X, Y and Z axis. A is going to represent you the edge length of unit cell along X axis, which is 0.48. B is going to represent you the edge length of unit cell along Y axis, that is 0.46 nm, and C is going to represent you the edge length of unit cell along Z axis, that is 0.40 nm. Now, what we are supposed to do, the coordinates of point P are given to us. These coordinates are Q, R, S. The value of Q is equal to 1 by 4. The value of R is equal to 1 and the value of S is equal to 1 half. Now, what we are supposed to do, by utilizing these values A, B, C and Q, R, S, means we are going to utilize the edge lengths of unit cell and the coordinates of point P. By utilizing these values, what we are going to do, we are going to calculate or we are going to find the position of point P in unit cell. Basically, the Q coordinate corresponds to the distance QA along x-axis. Accordingly, the R coordinate corresponds to the distance along y-axis and the S coordinate corresponds to the distance along z-axis. Accordingly, QA is going to represent you the distance along x-axis, then Ry is going to represent you the distance along y-axis and Sz is going to represent you the distance along z-axis. Q coordinate corresponds to the distance QA, R corresponds to the coordinate R corresponds to the distance RB along y-axis and S coordinate corresponds to the distance SC along z-axis. Then you are supposed to consider the distance QA. Then you are supposed to consider the distance RB. You are supposed to consider the distance SC so as to locate the point P. Now, the value of QA will be 1 by 4 into 0.48 nm, which comes as 0.12. We are going to locate this particular value from the unit cell as point M is going to represent the origin of unit cell, and along with this we are going to draw in further direction x direction to point N, which will be the length of QA along x-axis. Similarly, we are going to proceed for RB, which is the length along y-axis or parallel to y-axis. We are going to proceed the point from N to O, which is the length along the y-axis RB. And finally, we are going to position the SC. SC is the distance along z-axis, which is 0.20 nm units. parallel to z axis, and accordingly we are going to locate the point P with the coordinates q, r, s, that are 1 by 4, 1 and 1 half. This is the solution for the given problem. We have located the point P with the help of coordinates available with us. Now we will proceed further with the next point, that is crystallographic directions. A crystallographic direction is defined as a line between 2 points or a vector. The following steps are used to determine the three directional indices. First, a vector of convenient length is positioned such that it passes through the origin of the coordinate system. Any vector may be translated throughout the crystal lattice without alteration if parallelism is maintained. This is our first step. Second, the length of the vector projection on each of the three axes is determined. These are measured in terms of the unit cell dimensions A, B and C. This is our second step. Third, these three numbers are multiplied or divided by a common factor to reduce them to the smallest integer values. This is the third step. And the fourth one, the three indices not separated by commas are enclosed in a square bracket. Thus, u, v, w, the u, v and w integer corresponds to the reduced projections along the x, y and z axis respectively. For each of the three axes, there will exist both positive and negative coordinates. Thus, negative indices are also possible, which are represented by a bar over the appropriate index. For example, the square bracket is going to show you 1 bar 1 direction would have a component in the y minus y direction or negative y direction. Also, changing the sign of all indices produces an anti-parallel direction. That is, in square bracket 1 bar 1 1 bar is directly opposite to, in square bracket 1 1 bar 1. If more than one direction is to be specified for a particular crystal structure, it is imperative for the maintaining of consistency that a positive negative convection once established not to be changed. The square bracket 100, square bracket 110 and 111 directions are common ones. They are drawn in unit cell as shown in figure. We are going to repeat the process. A crystallographic direction is defined as a line between 2 points or a vector. The following steps are used to determine the directional indices. First step, a vector of convenient length is positioned such that it passes through the origin of the coordinate system. Any vector may be translated throughout the crystal lattice without alteration if parallelism is maintained. Step 2. The length of the vector projection on each of the three axes is determined. These are measured in terms of the unit cell dimensions A, B and C. Step 3. These three numbers are multiplied or divided by a common factor to reduce them to a smallest integer values. Step 4. The three indices not separated by commas are enclosed in square bracket. Thus, in square bracket u, v, w is the example for crystallographic direction. The u, v and w integers corresponds to the reduced projections along the x, y and z axis respectively. This is all about the crystallographic directions. Now we are going to see the reference part. For this session, the reference is William D. Callister Jr., David G. Rethwich, Material Science and Engineering, an Introduction. For further reading, you can refer this particular reference book for Introduction to Material Science and Engineering. Thank you.